Welcome to my presentation on the interior of Mars as seen by InSight. This presentation summarizes the work of many people, both in the InSight science team, many of which are listed below, but also the work of engineers, technicians, and other workers who helped us get to Mars. For those who don't know yet, what is InSight? InSight is a Discovery class mission, Discovery 12 to be precise. It was selected in 2012 as the first long-term geophysical observatory on another planet. The mission launched on May 5th, 2018 and landed in southern Elysium Planitia in November the same year. The lander is equipped with three main scientific instruments to investigate the deep interior of the planet. The seismometer SEIS, to record marsquakes and to investigate the crust, mantle, and core of Mars from it. It has been developed at IPG Paris and is operating continuously since January 2019. Then next, there's the radio tracking experiment RISE, which has been developed at JPL to measure core properties very precisely. This will be covered by Tilio Revoldini in the next presentation. And finally, there's the heat flow probe HPQ, the MOLE. This has been covered extensively in the press already and will not be mentioned any further in this presentation. An overview of the whole mission will be presented by mission PI Bruce Bennett in another session on Friday. So how do we use seismic recordings to get to the deep interior of Mars? It all starts with locating a marsquake, find out where it happened. For that, we use the fact that seismic waves come in two flavors. Primary P wave, which are longitudinally polarized and faster, and secondary shear wave, which are transversely polarized and travel a bit slower by a factor of 1.7. At the bottom, you see a seismogram of a marsquake that happened on Sol 235 of the mission. It is the second quake of this day, and hence it's called SO 235b. For this quake, the time difference between P and S was 170 seconds, or slightly less than 3 minutes. After we have identified these two seismic arrivals, we take a travel timetable. This has been computed before landing from interior models based on thermodynamic relations and reasonable assumptions about the composition of the planet. Of course, these models are preliminary and will be updated in the mission, but they serve as a good starting point to locate quakes. For this event, SO 235b, we obtain an epicentral distance of about 28 degrees or 1500 kilometers from the lander. So far, we have observed about 30 marsquakes for which we could estimate a distance, and around 12 for which we also could obtain a direction. This is the distribution of hypocenters as red circles over the planet. Gray lines mark event distances for which we could not obtain a direction. So as you see, many quakes happen in a region called Cerberus Fossae, but this is a story for another time. See the post of Anna Holston at the Marsquake service on Wednesday to find out more about how many quakes were recorded and how seismic data on Mars looks like. Going back to the interior. So we have located an event and we have a first estimate of its location. Now we need to extract more information from the waveform. We do this by identifying secondary arrivals, for example, surface reflected seismic phases, called double P, double S, and higher order multiples. These phases took a slightly different path through the planet and therefore depend differently on the velocity model of the mantle than direct PNS. What this means is that we can now compare the detected arrival time of the secondary phases with the prediction for a given distance and find mismatches. With PNS alone, we could not do this, since all their time difference told us was where the quake was. But now if we see a mismatch, we know that we need to update the velocity model. In this figure, you see that the different phases from the different quakes sample quite different depths of the mantle. So we can pose an inverse problem. Find one mantle model consistent with mineralogy on the one side that also predicts the correct P, double P, triple P, and so on arrival times. For one example of how this works, see these set of pre-mission models that are all consistent with mineralogy and thermodynamics. A common feature of many of those models is a strong negative gradient of shear wave velocities between 100 and 300 kilometer depth. This is directly related to the lithospheric thickness. The lithosphere is the very rigid uppermost part of the mantle that does not undergo convection, therefore has a much higher thermal gradient. This high thermal gradient, together with the low pressure gradient in the Martian mantle, translates into said negative shear wave gradient. This effect is much stronger for a thin lithosphere. And this negative shear wave gradient produces a so-called shadow zone, a distance range in which no S waves can be observed. Let's go back to the map and check where these pre-emission models predicted the S-wave shadow to be. For most of the models, it would be right between 20 and 40 degree distance, which, as you remember, is where we observe the bulk of our marsquakes. And since we did observe them, there cannot be a strong S-wave shadow zone in this distance. And what this means is there is no high thermal gradient thin lithosphere. The lithosphere must be thicker with a lower thermal gradient. So if we take information like that together with the travel times, we get models like this that have a very thick lithosphere of 450 to 550 kilometers, significantly more than on Earth. Here on Earth, the thickest lithosphere is found under ancient cratons and is less than 250 kilometers. This thick lithosphere is consistent with Mars as a single plate planet. From geodynamic modeling, we also find the need for a relatively high amount of radioactive heat-producing elements in the Martian crust, about 13 to 20 times more than the primitive mantle. From that, then, we can estimate the surface heat flow, which HPCube was supposed to measure, to be quite large, between 14 and 29 milliwatt per square meter. So now we have a good model of the upper mantle. Can we go deeper? Yes, but for this we need a new seismic observable, one that has actually seen the whole mantle and the core. And seismologists call this phase SCS, a shear wave reflected from the core mantle boundary. And indeed, we did find this phase in several marsquake records. Around 510 seconds after the initial P wave arrival comes an echo from the depth. The observation of this phase alone already tells us quite a lot. For example, if the core was solid, shear waves could just enter it and would not be reflected back or only in a small amount, below our observation threshold. Since we did observe SCS relatively clearly, we can conclude that the core cannot be solid, but must be fluid, a good reflector for shear waves. A fluid core had been highly implied from geodetic measurements such as the tidal love number K2 beforehand, but is now independently confirmed by the seismic data. So this is an example of core models using only the geodetic data. We can now use the seismic travel times together to jointly invert for that. If we take only the seismic data, we see that they infer a slightly larger core than the geodetic data alone. Taking both together, brings us to a core radius of 1830 kilometers with an uncertainty of 40 kilometers. And this has a strong implication. If the core is so large, there is no Bridgmanite lower mantle in Mars, which means that convection is relatively unhindered by this interface between the upper and the lower mantle that we find on Earth. Another thing is the core is large, around 54% of the planet's radius, almost the same ratio that we find on Earth, even though Earth is significantly more dense, even after correcting for self-compression. So what it means is that we need a very low density core, only around 6 grams per cubic centimeters. And this in turn requires a lot of light elements inside the core besides iron. Sulfur alone could not do the job. It would be required in completely unreasonable amounts, like 30%, to explain these low densities. So in the next step, we can actually update the composition of the planet as a whole. This is a recent study from Kahn-Liebsky et al., which inverted the geodetic, seismic, and other data for a new compositional model. Compared to previous models by Dreibus-Wenke, Taylor and others, these models have a significantly reduced amount of iron in the core, which then allows to increase the core density. In turn, this implies a high amount of volatiles, which implies an early formation of Mars. But of course, there are still a lot of open questions. For example, what if we actually did not observe SCS, but rather a reflection from a chemically distinct layer in the lowermost mantle? See a poster from Henri Samuel on Wednesday. In the next talk, Tilio Revoldini will present the independent estimates of core properties from the RISE radio tracking experiment. Daniela Antonangeli has a poster on Wednesday on geochemical and mineralogical constraints on the core composition. And finally, Scott King looks into the implications of the large core and the lack of a lower mantle on thermal evolution of the planet. So now we took a deep dive into the planet, but we forgot one significant layer at the top, the crust. To investigate it, InSight looks at converted and reflected seismic phases after the direct P and S arrival, which are caused by material contrasts below the lander. And an immediate result is that we find at least two very strong interfaces in all our analysis. The first is at 8 to 10 kilometers and transitions from very low seismic velocities, lower than the crustal velocities we find on Earth, to intermediate ones. Also, the second one is very clear in all inversions and was interpreted as the MOHO, the boundary between the crust and the mantle at first. However, a third layer exists in 35 to 40 kilometers, which is more in line with other estimates about the crustal thickness. Fundamentally, a too thin crust would not lead to the only very localized volcanism that we find on Earth today. For more estimates about the crustal thickness and mantle models as a whole, see the poster by Cecilia Duran on Wednesday. Now, the one absolute value that we have for the crustal thickness from InSight allows us to calibrate the global estimates of the crust that we have from gravimetry. And it results in a crust of just about 5 kilometer thickness in Hellas Planitia and up to 118 kilometers in Tharsis, with a global average of 55 to 60 kilometers. But the crust is not just interfaces, it's also layers in between. And this is where a second type of marsquakes brings a quite interesting result. These so-called high-frequency quakes. As you see in comparison to the low-frequency quakes below, the energy is sustained for much longer times as normal quakes. And this tells us something about the local crust and the region of InSight. These quakes really ring on for a significant time. And quakes that ring on for a significant time, that brings back memories from Apollo, the moon. We don't know yet where these quakes come from, but we have some reason to assume that it's not from the south of the dichotomy. So it's likely somewhere in the Elysium Planitia region, and the results are therefore representative for this part of Mars. To explain the waveform shape, we need to assume that seismic attenuation is very low and scattering is quite strong in the uppermost kilometers of the crust. The plot on the right shows the attenuation of Mars in red compared to various settings on Earth in blue and green, and to lunar data from the Apollo seismic experiment in gray. And what we find is that the uppermost crust must be much less attenuative than anything we find on Earth. And from lunar samples, such low attenuation could only be obtained by oven drying the samples until basically all the liquids was out. So wherever the crustal water is on Mars, it's most likely not in Elysium Planitia. For that, you see a poster by Foivos Karakostas on Wednesday as well, and a recently published paper by Sabrina Menina. So all in all, what did we learn? Mars has a large core, it's liquid, a high amount of volatiles in the mantle, therefore it likely formed early. It has a thick lithosphere, a rather thin crust, high surface heat flow, a high amount of heat-producing elements in the crust, and a very dry crust, at least in Elysium Planitia. And what is still open and what could be explored by the seismic data next? One question is, what is the extent of this dry crust? Is it really only below the lander or regional? What causes the crust layering, these interfaces in 8 and 20 kilometer depth? What causes the strong seismic scattering? Is it impact gardening like on the moon? So why is there no magnetic field despite the liquid core? And what is the composition of the core, and is there an inner core? This may be answered once we observe distant core traversing seismic phases. Is there chemical layering in the lower mantle? And finally, what exactly causes marsquakes if there's no plate tectonics? For the answer to those questions, stay tuned for the next extended mission of InSight.